Okay, so thank you for the introduction, and also thank to those that contributed to this awesome conference. I'm really glad to be here. So I will talk about uniform Martin's conjecture, but from a different point of view than the usual one. That is, from the point of view of single Turing degrees. So for this talk, when I say local, I will mean something that happens on a degree, very roughly speaking, while when I'm going to say global, I will mean something that happens on a cone. Just my personal way of speaking. Of course, cone in this context means an upward Turing cone, okay? So, a brief outline of what I'm going to say. So first, well, uniform Martin's conjecture was proved, so it's no more a conjecture, it's just the uniform version of Martin's conjecture, which is still open. And also Martin's conjecture is divided in two parts. So part one of uniform Martin's conjecture was proved by Sleiman and Steele in the late 80s. And what we are going to do in this talk is to show how to prove a local version of this theorem. I'm not saying yet what this means because I don't want to spoil my talk. Next, we are showing that we can deduce the original global version from the local one, just assuming Turing determinacy instead of full determinacy. So as a consequence, we are showing that over ZF plus DC, and actually over a way weaker base theory, Turing determinacy is equivalent to the statement of uniform Martin's conjecture part one. So then it will be natural to ask, what about part two of uniform Martin's conjecture, which was proved by Steele in 1983. So here we will ask, does this theorem arise locally too? And in particular, is it provable from Turing determinacy? Now, since there is some work on the meta-mathematics of uniform Martin's conjecture part two, the possibility of proving it from Turing determinacy would have remarkable meta-mathematical consequences. Okay, so to start, I'd like to tell you how I was led to consider uniform Martin's conjecture from a local point of view. So consider this structure. So the Cantor set with Turing reducibility. So of course, this induces us on any Turing degree a structure which is trivial because everything is in relation with everything else. But if you consider this, well, the reason for denoting it with this strange symbol, dot t, will be clear in a few minutes. For now, suffice it to say, this is the set of those triples made of a natural number e, a real x, and a real y, such that when you take the Oracle Turing machine indexed by e, and you provide it with Oracle x, that computes y, okay? We call this Turing reducibility via because when e, x, and y are when this triple is in this set, then we say that y is Turing reducible to x via e, okay? So when we consider this structure instead, a structure for Turing reducibility via necessarily has to be a two-sorted structure, because we need one sort for reals and one sort for natural numbers. Now, this structure induces on a Turing degree X the following structure, which is X provided with Turing reducibility via on the Turing degree X, which is which is not trivial anymore, right? So we have a little bit of the macrocosm and microcosm duality here, because we can consider a Turing degree from 2 points of view. We can consider it as an atom in the universe, which is something that you probably want to do when you consider the Cantor set with Turing reducibility, because there what you are basically interested in is the quotient structure, right? You two different elements that have the same Turing degree are just redundant, so you basically want to mod out by Turing equivalents and consider Turing degrees as your single points in your structure. But if you are interested in Turing reducibility via, you can also consider a single Turing degree as a universe itself, right, with its own structure. So you may want to ask, how complicated is such a structure? And how does the complexity of the structure depend on the Turing degree X? So for example, is it the case that the more complicated X is as a Turing degree, the more complicated that the structure on X will be from a structure theoretic point of view? So for example, let's phrase this question in a more formal way. Is it the case that the structure we have on X is embeddable into the structure we have on Y if and only if X is Turing reducible to Y? So the answer is yes, and that's what we are going to prove. But the interesting thing here is that this doesn't always happen for all kinds of similar reducibilities. For example, I could have said the same consideration for the arithmetic degrees. I could have talked about arithmetic reducibility via, and but this time I would have said that the answer is no, because well, implication one implies 2 would hold even in this case, but there are arithmetic degrees X and Y such that arithmetic reducibility via on X is embeddable into arithmetic reducibility via on Y, but we actually have no arithmetic reduction from X to Y. Okay? And the interesting thing is that the key to prove this theorem 1 is to pass through a local version of uniform Martin's conjecture part 1, because the first two facts are equivalent to a third one, which is the existence of a non-constant UTI function from X to Y, and the equivalence from between 3 and 1, in particular the implication 3 implies 1, can be regarded as uniform Martin's conjecture part 1 from the point of view of the degrees X and Y, as we are going to argue. Okay? So I now have to tell you what, maybe in precise term, what what is an embedding between these kind of two sorted structures. So, well, if you have X and Y subset of the Cantor set, you define Turing reducibility via on X, as it is obvious to do, right? It's a restriction as a relation. Then an embedding from these two structures is, again, what you expect. Because when you have ordinary one-sorted structures, an embedding is just a function that preserves the truth of atomic formulas in both directions. Now you have two sorts, so an embedding will be a pair of functions, one for each sort, with the condition that this pair preserves the truth of atomic formulas in both directions. That means equality between objects of the first sort has to be preserved in both directions, which means f. So the first function has to be injective. Same for objects of the second sort. So the second function has to be injective too. And finally, this relation, in this case, Turing reducibility via, has to be preserved in both directions, right? And a morphism, or a homomorphism, if you prefer, would be the same thing, but this time you want this pair to preserve the truth of atomic formulas just in the forward direction, right? So this amounts to say this, okay? The only thing here is that this notation is a little bit awkward, so we are, oh, let me just tell you. Such an f which admits a function u that does that job is said to be a uniformly order-preserving function, or just UOP for short, and the function u will be said to be a uniformity function for f, right? So I just want to pick a more handy notation. So I will say that I will use that dot as a notation for a partial binary function. So I will say that E dot x is either f with oracle x and index e, if this is in the Cantor set, or will be undefined otherwise. And I will write this Kleene equality instead of saying that this triplet is in the set, right? So Kleene equality, as usual, means that both sides of the equations, well, I mean, if either of the two sides is defined, then the other has to be defined as well, and they have to be equal. So with this notation, I can rephrase the condition of being UOP, saying that f from x to y is UOP if there exists a function u from natural numbers to natural numbers, such that for all natural number e and x1, x2 in the set x, well, as before, the pair fu preserves Turing reducibility via in the forward direction. But with this notation, we can also have this handy formulation. That is, if E dot x1 is defined and is in x, so it is equal to some x2 in x, then we can take f of this guy, and this is Kleene equal, so it's equal because it's defined to this thing here, right? So we can take the index e out of the function f, provided we transform it according to u. So now I want to define Turing equivalence via. So I say that x and y are Turing equivalent via a couple of indices I and j, if y is Turing reducible to x via e, and x is Turing reducible to y via j. And here we use the binary function notation as well. Okay, and we have this. And we can define a function f from x to y to be uniformly Turing invariant if there is a function from couples of natural numbers to couples of natural numbers, which this time preserves Turing equivalence via in the forward direction. Okay? And here again, we can rephrase this in this way. So, okay, the last trivial thing to observe is that UOP implies UTI. And now we can see a proof of theorem 1. So, implication 1 implies 2 is really easy because you just pick an element inside of Turing degree y, call it light phase y, and you can define the function f to map a z to z join this light phase y. And this will be well defined. I mean, z join light phase y will in fact be in the Turing degree y because of the hypothesis that x is Turing reducible to y. Okay? And now if you define the function u to send a natural number e to the obvious natural number that gives you the following implication, then if your obvious guess was the right one, you will also have the converse implication, and so that couple of functions f and u will be an embedding, okay? Because they are trivially seen to be injective too. Now, 2 implies 3 is even more trivial because if you have an embedding, then f will be UOP and hence UTI, and f will be injective and so non-constant. So the non-trivial implication is 3 implies 1. For this, we need 2 lemmas. So lemma 1 is that if x is a Turing invariant set, that means is a set closed under Turing equivalence, and we have a function from x to the counter set, which is UTI, we can always pick a computable uniformity function for u. This is the first lemma that unfortunately I'm not going to prove because of reasons of time, unless I have a lot of time left. And lemma 2 is a really classic one. If you have 2 sequences of natural numbers y and z, and you take phi with oracle y and index z of n, and you take the join for all n, you have something that is Turing reducible to the join of y and z. Now, this could be a partial function, actually. But anyway, whatever it means it will be, there is some thorough acceptation by which it is actually Turing reducible to this. But anyway, it doesn't matter because we are going to apply this lemma when this is well defined, it's an element of the counter set, so there will be no problem. So we can assume as an hypothesis that this is a sequence of natural numbers. So the proof is trivial. Maybe I should just mention that the join is taken by putting these elements, these reals, supposing they are reals, we put them as columns of omega times omega matrix, and then we turn this matrix into a sequence using a pairing function, right? So then we take, we basically take a universal Oracle Turing machine, and this will do the job. So there's nothing, the only thing I want to point out here is that this is the crucial point that makes theorem 1 work in the Turing case and makes it fail for the arithmetic case, because we don't have any universal arithmetic reduction, okay? So here we go with the proof of 3 implies 1. So I recall that the hypothesis is that we have a UTI function from Turing degree x to Turing degree y, which is not constant. So we can choose 2 different elements that are mapped to different elements. What we want to prove is that x is Turing reducible to y. Okay. Now, there is a computable function R such that phi with oracle x and index R of n is either x or z, depending if x of n is either 1 or 0. Can you all see this? Yeah? Everybody? Okay, great. Then there is a natural number e such that phi with oracle x and index e is the same as phi with oracle z and index e, and this is x. Okay? So just tell me if I have to explain, but yeah, it's very easy to see. So we have a computable function from omega to omega square that maps n to Rn and e. We call this t. So t is a computable function, and we have this, right? So if we take f of both sides of this equation, we get this. And now f of x and f of z are different. So suppose they differ on the kth digit. So what we have, if we take the join of all these guys for n, so we have this, the way the columns in this join alternate will follow exactly the way the digits of x alternate, right? So if we take the kth row of this matrix, this will either be x or 1 minus x. So x is Turing reducible to this join. We can rewrite this guy here as this guy here using the fact that f is UTI. So we choose a uniformity function for it. And by lemma 1, we assume that such a uniformity function is computable. then we can rewrite this as this by its definition, because it's defined, and when it's defined, it's just this where pi is the projection on the first coordinate. So we are using just the basic fact that when you have ij, this dot here of y, this is either undefined or it's phi I of y, which is phi projection of ij. So we are using this. And finally, by lemma 2, this is computable in the join of f of x and the composition of t, u, and pi. But t is computable, pi is computable, and u is computable by lemma 1. So this is computable in f of x, right? So what we have proved is that if we have a function that goes from the Turing degree of x to the counter set, UTI, then either f of x can compute x or f is constant. So now compare this theorem with the uniform Martin's conjecture part 1 proved by Slayman and Steele. Now you can see that this really looks like a local version of this theorem, right? So next thing that I promised to do is to show you that we can deduce the global version from the local one using just Turing determinacy. So what we have to do to prove the global version, so suppose we have f, which is UTI on a cone. So a cone, say, C. Consider the set of all x in this cone such that the function f is constant on the degree of x, right? By construction, this is closed under Turing equivalence. So by Turing determinacy, it either contains a cone or its complement does. So if the complement contains a cone, of course we can assume this cone is already contained in C. Otherwise, just take the intersection of these two and choose a new cone inside this intersection. So if we have this cone D, for all x in D, f will be constant on the, D is in the complement of A. So f will be non-constant on the Turing degree of x and will be UTI on it. So by the previous theorem, f of x is able to compute x. Otherwise, if A contains a cone, we can apply this lemma here that tells you that under TD, if you have a function that maps Turing degrees into singletons, this will be literally constant on a cone, right? So we're done. I don't think I have to prove this lemma. This is really a classic and easy argument regarded as folklore generally. But maybe Slayman and Steele are maybe credit goes to them, because the first time I saw this argument, it was on the Slayman and Steele's paper in the form of a remark that under AD, there is no choice function on degrees. So maybe credit goes to them for this. Okay, so next thing I promised to do is to show you that over ZF plus DC, TD is equivalent to the statement of uniform Martin's conjecture part 1. But now we have two different statements because the original statement said that constant on a cone means constant up to Turing equivalence on a cone. Now we proved it saying f is literally constant on a cone. But anyway, both statements are equivalent to TD under ZF plus DC. So what we have just done is to prove that 1 implies 2. 2 implies 3 is trivial because, of course, literally constant on a cone implies constant up to Turing equivalence. And 3 implies 1 is also easy because if you have that A is closed under Turing equivalence, you can define f, a function f like this. Of course, f is UTI because every time two things are Turing equivalent, no matter via which couple of indices, their images will be equal. So you have no problems at witnessing that they are Turing equivalent. So it's trivially UTI, and it cannot be that it's increasing on a cone, so it must be by hypothesis constant on a cone up to Turing equivalence, but it follows that this means that either A or its complement contains a cone, okay? So now we finally arrive to the question, what can we say about part 2? Can we, first, I have to introduce some just little pieces of notation. So when we have two functions, you say that, well, this less than or equal m means Turing reducibility on a cone. The jump of a function is just its pointwise jump. And the increasing on A means that f of x computes x for all x in A. So uniform Martin's conjecture part 2 is this statement, which was proved by Seal. So assume AD, the set of those functions which are both UTI and increasing on a cone is pretty well ordered by this less than or equal m. And for all f in J, there is no G in J that lies strictly in between f and its jump. Okay. So does this theorem arise locally? That means, is it derivable from some property that UTI function exhibit on single degrees? And also, is it provable from Turing TD alone? Now, since Chong, Wang, and Yu proved in 2010 that part 2 of projective uniform Martin's conjecture is equivalent to projective determinacy over ZFC, this would have the, well, remarkable meta-mathematical consequence, because if in particular projective uniform Martin's conjecture part 2 were provable from projective Turing determinacy, we would have that projective Turing determinacy is equivalent to projective determinacy, which would be, you know, a really outstanding result. So we are really interested in this possibility. But let me go back. I had no idea on how one could approach uniform Martin's conjecture part 2 locally. But there is a different proof that was given of this theorem, which is Becker's proof, which passes through a nice, effective descriptive set theory. And I thought that maybe that could be the key to prove a local version of this theorem. So I have to tell you what point class jump operators are. Well, I'm not going into the details because I should tell you what a reasonable point class is. I don't want to tell you the details, but anyway, suppose we know what this property of being reasonable means. We have this point class gamma. We say that f is a gamma jump operator if f of x is the universal gamma relativized to x subset of omega. But maybe it's better if I make some examples. It will be clear. So for example, the function that maps x to the alpha iteration of the jump of x is a sigma 0 alpha jump operator for all countable ordinals alpha. Of course, this will be defined just not everywhere for arbitrary alpha, but it will always be defined at least on a cone, at least on the cone above a real that codes alpha. And this is the sigma 0 alpha jump, because this is the universal sigma 0 alpha relativized to x subset of omega. And for example, x that gets mapped to the relativized to x clean is O is the pi 1, 1 jump operator, because this is the pi 1, 1 relative to x subset of omega. So what Becker proved is that if you assume AD and you have that f is UTI and increasing on a cone, then f is either equivalent to the identity on a cone, or f is a point class jump operator on a cone. So one can deduce part 2 of uniform Martin's conjecture from Becker's theorem using the fact that these reasonable point class are organized in a well-ordered hierarchy. So maybe we could try to prove Becker's theorem locally. And here is my my proposal. So to work locally, we have to fix a degree x. Now consider the smallest family, call it u of x, of those functions whose domain is x, that contains constant functions, the identity function, and the complement function, if you think of x as a set of natural numbers. Then put all point class jump operators, which are defined on x, and close this family under precomposition with computable isomorphisms and finite and infinite joints. Of course, if you have closure under infinite joints, you will also have under finite joints. Now, of course, every function in this family is UTI, and indeed UOP, but I ask the converse. Is every UTI function defined on the Turing degree x in this family? So what I'm asking here is, in this family UX, we have all familiar UTI function. I'm asking if there are some, if there exists some weird, some exotic UTI function defined on X that doesn't have anything to do with these familiar functions that we know, that can't be obtained from these ones, okay? So I actually don't know if I'm trying to show that a positive answer to this question would lead to a proof of Becker's theorem, But I don't want to talk about this now because it's a little bit of work in progress, so it also might be wrong. What I want to talk about is that anyway, it really shares the same spirit of Uniform Martin's Conjecture Part 2, because the true intent of Martin's Conjecture Part 2 was to give mathematically, to formalize in precise mathematical terms the idea that natural Turing degrees, that is, those Turing degrees that are commonly found in practice and that seem to be the most natural ones, are in fact well ordered by Turing reducibility, and that in this well order the successors are provided by Turing jump. Okay. So the idea behind the formalization is that a natural Turing degree should be definable, and its definition should relativize to arbitrary oracles. And so this relativization process would lead to a nice definable increasing TI function, right? And yeah, but you have a problem. You could patch together several definable functions into a single definable function. So you would have a lot of hybrid function, which it's not clear what they should represent. So how can you get rid of the hybrid function that you could get? The solution to this problem is that under AD, if you patch together several pieces, well, actually, one of these pieces has to prevail on a cone. And so, if you mod out by Turing equivalents on a cone, you get rid of hybrids functions, and you just get the fundamental ones, right? So the underlying question is if point class jump operators are the only fundamental ways to increase the computational content of Turing degrees. Actually, this is the content more of a stronger conjecture, which is Steele's conjecture, that says that every TI function under AD is actually UTI, and so via Becker's theorem is really a point class jump operator up to equivalence on a cone. But what I claim is that this is also the underlying question of my question here, but just on a different level. Because instead of being formulated in the macrocosm, so where your atoms are Turing degrees, and so you have definable functions on degrees, you look at what happens on a cone, and so on. You take the microcosm approach, so now your universe is just a single Turing degree, which comes with its structure. So the functions that you want to consider in this context are the function that preserves some of this structure, which are the UOP functions, or if you require something less, the UTI functions. And so by asking if every such function lies in this family, we are really asking this question: are point class jump operators the only fundamental ways to increase the computational content of Turing degrees? You're just asking on a different level. And yeah, this was actually a question for you. So it was more a call for arms than a question. And yeah, I'm actually done. So thank you for your attention. Yeah. Oh, yes. This was Lemma 1. So I expected that question. I'll prove it first in the case where f is UOP. Okay? Then I will proceed with the proof of the UTI case. So you first have to consider the obvious operation that gives you this, right? This is what you have when, you implicitly define it when you have to show that Turing reducibility is transitive, okay? I call this Turing multiplication. The important thing is this is a computable function, okay? It's associative, and if this is defined, well, then you have that this is the same as this. So the dot and Turing multiplication have this kind of associative property that is, it really looks like the properties that is satisfied by group actions, right? But here you just have a semigroup, actually a monoid, and this is not always defined. So this is the difference. Now, suppose f is UOP and take V a uniformity function for it. Consider these three Turing reductions. So C appends a 1 in front of X, B appends a 0 in front of X, and then what A does, it first counts how many zeros there are before the first one, calls it E, and then it starts acting as the reduction numbered by E on the rest of the oracle. So, okay, I use this shorthand for Turing multiplication. I denote it the same way as ordinary multiplication. So what we have is that by how I defined E, this is the same as this, right? Now, if this is defined and if in X is in X, I want to show you that I can take E out of F provided I transform it according to U, with a U a computable function. So what I do is the following. F of E will be the same as this. Now I apply the associativity of this multiplication and the dot, and I use the fact that BE times C dot X is still in the domain of the function, because the domain is closed under Turing equivalence. So I have this. I repeat this for all of these guys, and I arrive to this, right? So now I'm done, because I define UE as this guy here, and what I have is that f of E dot X is this. So this tells you that U is a uniformity function for f, and u is computable. Because Turing multiplication is computable, you get e. These are 3 fixed natural numbers, and so you are done. And for the UTI function, it's, well, your u will be this. It's a little bit more complicated, but the idea is really the same.
How is compute the level by level analysis?
So,
how you compute the level by level?
sorry, I didn't get
How you compute level by level?
level by level? What?
Because the order preserving part for how you compute order consider the function of order preserving function.
Yes.
And I remember when we do term one you compute for order preserving.
Oh, yeah.
You need a really fine structure.
Yeah.
And you said your proof is better, so.
No. My proof of what is better? No, I don't have a proof about part 2. Part 1 is what I have proofs about. Part 2 is just I was like thinking about what one could do in the local approach, but I don't have anything. So I have a lot of pauses here, so maybe. Okay. You're talking about this? Yeah. There's actually a finer way of phrasing this original theorem. It's level by level. It was a quicker way to say it. Thank you.